This conference will now be recorded.
Okay, in today's class, we are going to discuss about losses and efficiency of a single phase transformer. So already we discussed the equivalent circuit parameters and the OC/AC test of single phase transformer, right? And the purpose of OC and AC test is to find equivalent circuit parameters, losses, and efficiency regulation. Now we are going to discuss about what are the losses available in the transformer and what will happen if the losses is occur in the transformer. How we can minimize that losses. So that is the topic we are going to discuss in today. So let's move on to the topic. And this is topic useful to solve the problems based on losses of the transformer. So in your external exam they may ask problems based on the losses, and you had to follow these formulas, then you can solve the problem, right? We already discussed, right? In transformer we have only electrical losses. One is iron and next one is copper losses. Here these two losses based on the different parameters. If you see which if you see the iron losses should be, it is depends on that what type of material we are using and how the construction is happening. So the iron losses is again two types. One is hysteresis and eddy current losses. The combination of these two we can call it as iron losses, and it is called as constant losses. Why it is called as constant losses? Why iron losses we call as constant losses? Is there any reason why we can call as iron losses is the constant losses? And similarly, why we can call as copper losses is a variable losses, right? So the iron losses is independent on the load. So if the load, whether the device is connected to the load or not, it is won't bother. So the iron losses is, it is completely independent of the load. That's why we can call it as a iron losses is a constant losses. And here copper loss is completely depends on the load. So what is the load we are applying on secondary, that much of copper loss will be happening. So because the copper loss formula is I square R. So when the load is keep on going to be increased, it will drags the more current. When the current is increased, copper loss also increases. That's why the copper loss we can call it as a variable losses. The reason is it is completely depends on the load. Now we are going to discuss the losses happen in the transformer with respect to the load and without load, and finally we are finding the efficiency, right? See what is the why we are calculating the losses for finding the efficiency means already we know the efficiency formula, that is output divided by input. Now how we can write this equation in terms of electrical energy, in terms of electrical form? I want this efficiency equation in terms of electrical form. How you can write? See, if you take that motor, the efficiency we can write input minus losses divided by input. This is the efficiency formula for motor, because for motor we are applying the input is electrical energy, right? So that's why I'm going to represent this entire equation in terms of electrical form. Similarly, for generator, I can write output divided by output plus losses. For generator, the output is electrical energy. That's why I can represent efficiency of generator in terms of electrical form. Now, at the same time, how we can represent efficiency for transformer in electrical form? Which formula we can use? Whether it is or this one. Which formula we can use? So I need efficiency formula in terms of electrical form. Which formula you can use? This one, input minus losses second. Then, so why can't we use first formula? First formula you choose for. For transformer, we can use both equations. Input minus losses divided by input, or output divided by output plus losses. Because for transformer, both ends we are getting that electrical energy. But while calculation point of view, always we can choose that second equation, because it is very convenient to calculate this output when compared to the input value. So we can use both formulas, but our convenient purpose we can use only second equation, that is output divided by output plus losses, right? So are you clear about efficiency equation? Now we'll see that what are the losses available in the transformer. Right. See, if you see that transformer, its output rating is always represented in kVA, kilovolt amperes. This is the power rating of a transformer. So if you take that motor and generator, its value is its power rating should be represented in the kilowatts. What is the reason means, if you see that generator and motor, if there is any power factor as available here, so you are all did the calculations in generator and motor, right? In that part, you studied any power factor here? Is there any using of power factor in motor generator calculations? You did the Swiman test and the brake test. In that experiment, you can see that power factor value. No, right? So if you take that transformer for calculations, it can be included by the power factor. So where the power factor is included, there we can represent that power rating in terms of kilovolt ampere. That is the one reason. And second reason is, in transformer we are getting the two losses. One is iron losses and copper losses. In that, iron losses is caused by that voltage, and copper loss is caused by the current, because copper loss formula is I square R. So based on the current, its losses will be increased. That's why the transformer rating is always representing in the kVA, kilovolt ampere. Right. Now, if you see this in electrical system, we have three types of powers. One is apparent power, real power, and reactive power. See, apparent power we can represent in terms of VA, volt ampere. Wait, I will take that another color, then you can see. See, we have the three types of powers. One is apparent power. Next, second one is real power, and it is also called as active power. And next one is reactive power. So the apparent power is always represents volt amperes, and real power is always represents in terms of kilowatts, and reactive power in terms of kVAR, VAR. Okay, now, this is the units of apparent power, real power, and reactive power. Apparent power, that is P is equals to VI. So we can represent P is equals to VI. This is called as apparent power equation. For real power, we can represent P is equals to VI cos pi. So this is the equation represents that real power and active power. And for reactive power, we can denote its equation is Q and its value is VI sin pi. This is the representation of reactive power. So we have three types of powers. P is equals to VI, P is equals to VI cos pi, and Q is equals to VI sin pi. These are the three powers. Now let us see that how we can calculate these three types of powers in transformers. Right. See, there is not a rated in watts because of in transformer the losses should be happened by one of the losses from the voltage and other losses from the current. So here the load factor is the load power factor is unknown value. So we don't know the value because we are if using that inductive load. For inductive load, what is the power factor value? It is lagging or leading for inductive load. We have three types of load, right? Resistive load, inductive load, and capacitive load. For resistive load, we have unity power factor. What about inductive load and capacitive load? For inductive load, we have right. For inductive load, we have the lagging power factor. For capacitive load, we have the leading power factor. Generally, the power factor cos pi is equals to 1. Okay, na? Right? If it is lagging power factor, it should be less than 1, but we don't know the exact value of power factor. So it should be less than 1, but we don't know exact value. Similarly, if you are using the capacitive load, it is greater than 1, but we don't know the exact value. So when we don't know the power factor, there we can use that apparent power, and it is generated by S is equals to VI. So next, reactive power, that is real power. So what is the real power? P is equals to VI cos pi. So I already told you, right? And here VI is nothing but a apparent power S, and this one is power factor. So this is the representation of active power or real power. So keep remember these formulas. So S is a apparent power and it is equals to V into I. And active power, it is also called as real power and it is represented by VI cos pi. Next. Now from this equation, we can calculate that what is the value of S. S is equals to active power divided by power factor, right? So if you are using that, so already you seen in the OC and AC test, right? In OC test, we have the power factor is 0.2. For AC test, we have the power factor is 1. So you know the value of power factor, right? At that condition, you can calculate the apparent power. So S is equals to active power divided by power factor. Now let me see one example problem on this active power, that is active power and apparent power calculation. Now this is the question. We have the V1 value and V2 value and S value. Then find the power output at unity power factor. Right? See, P is equals to VI cos pi. This is the power. And here VI we can represent S and cos pi it is equals to 1. So S into 1. What is the S value here? 2 kVA. Now let me see that what will be the answer. So this is the value of power. So I already told you that for apparent power, the units of power is VA. For real power, so apparent power we can represent in S by S. For real power, its units is kilowatts. For reactive power, we can represent kVAR. Okay, now we are finding that power in terms of kilowatt. So when the kVA is multiplied with power factor, then you will get that kilowatts. Okay, now 2K, that is the S rating is 2 kVA. It is already given here, and the power factor is 1. Finally, we will get that P is equals to 2 into kilowatts. This is the real power. Next, what is full load secondary current at 0.8 power factor? Now let me see that. So for the value of power, the power equation is P is equals to VI cos pi. So this is the value of right, and here I is equals to P divided by V cos pi. What is the power rating of transformer here? In this circuit, what is the power rating? So this is the primary voltage, secondary voltage. What is the power rating of this transformer? Two. That is 2000 volt amperes. So already you've seen that for AC test. Okay, now similarly, and V into cos pi. So V will get cancelled. 2000 divided by 0.8. Then we will get that current. Okay, now. So let me see that. See, 2000 divided by 230 into 0.8. See, for unity power factor, we got that 8.69. But here we have the power factor 0.88. Then the current is becomes I is equals to 10.87 amperes. So this is a simple problems you may get for 2 marks here. Now let me see that one more problem. So we have the primary voltage is 1270 volts and secondary voltage is 200 volts, and its power rating is 20 kVA. Then what is the power output at unity power factor? So just do this problem, then find the value of output. So its formula is P is equals to VI cos pi. P is equals to VI cos pi. Then find the power output. What is the value of power here? What you will get? So its formula is P is equals to VI cos pi. And this is the apparent power, right? So P is equals to S into power factor. Here S rating is 20 into 1000. Its power factor is 1. So finally we'll get 20 kilowatts. That is the real power of this transformer. Let me check that answer. Right. So this is the answer for this problem. P is equals to 20 kilowatts. Now find this value of power for 0.8 power factor. What is the value of power output at 0.8 power factor for this given transformer? Same formula, you have to use the same formula, that is P is equals to VI cos pi. and here VA is nothing but a S, that is 20 kVA, 20 into 1000 and 0.8. Then what is the answer here? What is the answer for power at 0.8 power factor? Right. So its answer is 16,000 watts or else 16 kilowatts. Okay, now let me check that answer. Right. So this is the answer for this problem. Next. What is the full load secondary current at unity power factor for this given transformer? Find them. Find out the secondary current. Formula is I is equals to S divided by V into power factor. So S is 20 kVA and the secondary current. So we have to apply that secondary voltage, that is 200. So 20 kVA divided by 200 into 1. I is equals to 20 into 1000 divided by V is 200, right? 200 into 1. So 2 get cancelled, and what is the answer for current? Hundred amperes. Yeah, right. So this is the answer for C here. If you observe that primary has the more voltage and secondary has the less voltage. So I already said here in the transformer the voltage and current relation is inversely proportional. If the voltage is high, current will be low. If the voltage is low, current will be high. So here the secondary voltage will be low. That's why we got that secondary current is more value. Now from this, how we can calculate the primary current? So find the primary current from this value. So we know the value of V1. V1 is 1270. And we know the value of V2, that is 200. We know the value of I2, that is 100 amperes. Then how we can calculate that I1 value? So by using which formula we can use primary current? Which formula we can use here? Right. So from the transformation ratio, we can calculate this value. So what is the transformation ratio? V2 divided by V1 equals to I1 divided by I2. Now from this I need I1 value. So I1 equals to 100 into 200 divided by 1270. Then find the value of I1. $200 divided by 1270 into 100. What is the value of primary current? Right, 15.74 amperes. So this is the way of calculating that different powers and different voltage values and current from the given transformer with respect to the given power factor. Right, we'll see that how we can calculate the efficiency. No. So the efficiency formula will give the relation between input power and output power. So this is the formula for efficiency, that is output power divided by input power, and we can represent input is equals to output plus losses. So from this we can write efficiency formula is output divided by output plus losses. So this is the formula we can use mostly because we can easily calculate that output value based on the power factor. So if you know the power factor, you can easily calculate the output power. And in terms of input, we can represent efficiency is equals to input power minus losses divided by input power. And this is in terms of output power. So you can use both formulas based on what you know the value of parameters, because in transformer the sending end and receiving end both are electrical form. So that's why we can use both formulas based on our convenient. See, generally the efficiency of the electrical device should always represent in terms of percentage. So if you compare efficiency for that motor and generator and transformer, which device having the more efficiency among these three? So I already said in starting classes, when compared to motor and generator transformer, which one has the more efficiency and what is the reason? Right. What is the reason why transformer has the more efficiency? So why transformer having the more efficiency? Is there any reason for this? Right. So here, sorry, you can't say negligible. So here the mechanical losses are absent. So there is no mechanical losses, right? When the losses are reduced, we can get that more efficiency. Generally, in real time, the efficiency of transformer is we can get 90 to 95%. In the inverse, no electrical device should give this type of efficiency. So only the transformer will give that efficiency is in between 90 to 95%. So that's why we are giving more protection on the transformer because of this reason. Right. See here, this is the power flow of the efficiency. For transformer, we are getting that power input and power output with 100% efficiency. In out of 100% efficiency, we will get some losses, like this power losses used to reduce that iron losses, and this is the power we can use for copper losses. Because of these two losses, the 100% of efficiency should be reduced to 90 to 95%. This is the reason why the transformer efficiency is not 100%, because of in out of 100, some of the power overcome by that iron losses and some of the power overcome by the copper losses. That's why we are getting that less than 100% efficiency. Right. See, for this problem, how we can find the output of transformer? So then find how we can find the output here. Which formula we can use here? So the efficiency we can write efficiency is equals to output divided by input. From this you can calculate that output power, output of a transformer. Let me see that how we can expand this formula. So here we know the value of efficiency, right? 90%. Then how we can represent that input power? See, the power is given by S into power factor, and the power we can represent 100 into 0.85. So the power is 85 watts. So this is the value of finding that output power. Next, how we can calculate the input power? From the efficiency. So if you know the value of efficiency and input output power, then input will calculate output divided by efficiency. So this is the value of input power. So you need again this problem. So I will show you again. So this is the first question. How we can calculate that power output of a transformer? See, the power output we can represent S, that is P is equals to VI cos pi. P is equals to VI cos pi. So here VI is the apparent power, right? That is S. P is equals to apparent power. The given, sorry, here 100 is so it is wrong answer. The P is equals to S is 20,000 into 0.85. So what you will get power here? 20,000 into 0.85. So 200 into 85. Then what is the value? 2 5s are 10, 2 is 16, 7, 1700. So 17 kilowatts. That is the output power of a transformer. Now by using this output power, we can calculate the input power by using this formula. So already we know the efficiency value, that is 90%. So if you eliminate the 90%, what is the value here? 0.9. So input is equals to 17 kilowatts divided by 0.9. Then we can calculate that input power. Right. Now we'll see that how we can find the losses. See here, the losses formula we will get from input is equals to output plus losses. Now here we know the value of input and output, then we can calculate the losses by using this formula. Say I will send this PPT in classroom, then you can solve this problem. Right. Now let me see that what are the losses available in the transformer. The first one is copper losses. It is completely vary with load. Okay now. See, this is about copper losses, and this losses should be vary with the load current, and it will produce the heat created by the resistance of windings, and short circuited supplies copper losses. See, if in OC and AC test, we are getting the copper losses in only AC test, because when the secondary is closed, then there is a flow of current. Due to the flow of current only, they will get that copper losses. Right. So this is the four terms regarding that copper losses, and this losses makes that heated up of a transformer. Now this is the experiment. It is short circuit test. Now here we can observe that current here. What is the flow of current in secondary? Now from this current we can find that what is the copper losses occur in the secondary current by using this formula, I2 square into R. So this is the formula for copper losses. So when the secondary is short circuited, the power losses shown by the voltmeter shows that copper losses. And here this copper loss is the full load copper losses. Now we have to find copper losses at different loads. See, if the full load copper losses is 100 watts. Then what is the copper loss at 1/4 load? So at 1/4 load, its value is 1/4 whole square into 100. For half load, 1/2 square into 100. Why square term will come here means because the load is directly proportional to the current, right? So for copper loss, we have the formula is I square. So that's why we are going to be squaring on for the load side, that is 1/4 square. Now let me see the one example here. So this is the full load copper loss when the transformer is loaded at 50%, that is half load. Then what is the value? Copper loss at half load is 0.5 square, that is 1/2 whole square into 100. Then you will get that load at the copper losses at 1/2 load of a transformer. So this is the copper loss value. And now if you see the graph, the copper loss, you will get that like this. See here the x-axis represents that current and y-axis represents that copper losses, right? See, for example, if you take that graph, it should be keep on going to be increased, because when the load is keep on going to increase, the copper loss and current also increases. So this is the graph represents that how the copper losses will be happening in transformer with respect to the load and load current. See here, for 50% of load, that is half load, how much of you are getting the losses? 25, right? So for 100, so when the load is completely 100%, then we will get that 100 copper losses. Now let me see that iron losses. Here the iron losses is permanent, that is constant value, because it won't depends on the load, and it is always present whether the transformer is connected to load or not, and it is related to the transformer construction, because I already told you that iron losses is the combination of hysteresis losses plus eddy current losses. Here this eddy current losses should be depends on that laminated construction, and hysteresis losses depends on the type of material. Now let me see these two separately. The first one is eddy current losses. See, these eddy current losses should be minimized by using laminated construction, and these losses will be produce heat. Now hysteresis, and this is the value reduced by using special steels in lamination, that is it should be depends on the type of material. So this is the way, this is the experiment we are going to find that iron losses, that is open circuit test. So open circuit test means we are conducting this OC test on low voltage side, and high voltage is open circuited. Now what is the value shown by the wattmeter, that is represented as iron losses in the transformer, right? Okay students, this is about losses and efficiency of a transformer. Now I am going to end this class now. So I will upload this PPT and video in Google Classroom, then you can go through that. So I am going to end this class now. Thank you.